All right, you ready for chi-square?
Yep.
Tonight we'll do the chi-square test. I think it's a fun topic. It's not that difficult. It's also an interesting summation of some other things we've done. So the chi-square test, the chi-square test statistic, it tests things that we've learned in other ways. But it's just a more succinct way to do a lot of things. It's a commonly used statistical tool. You'll hear statisticians, people giving a regression report, people talking about population proportions. They'll say, I ran a chi-squared test and it is statistically significant. And no one argues with them, because no one knows what they mean when they say chi-squared, but you will all know what they mean when they say chi-squared. You know how to use it yourself. All right.
We could call it BS.
What's that?
We could call it BS.
No, it's a legitimate test. It's you can call their BS. Yeah. Oh, good point. You can call their BS, not the chi-square. All right. So we're going to go through an example, which is going to put the chi-square test in perspective for us, and then I will explain with some slides how we support all that. Then we'll do another example, and then we'll be done. So not a whole lot. Let's look first at this example, and then I will ask which questions we could ask about this data. All right, so suppose we are interested in finding out whether or not Mercy College MBA program, the Mercy College MBA programs, provides an adequate selection of course offerings.
No.
All right, so you say no. Where do you spend most of your time? The Bronx, Dobbs Ferry, or Manhattan?
Everywhere, because there's not enough.
Yeah.
Yeah.
All over and online. They're missing it online.
Yeah.
Okay. Would you say your home base is the Bronx?
Jobs.
For this,
Dobbs?
yeah, for this quarter.
Next
And
quarter,
then
yeah.
next
But
quarter it's like split.
I
between
think
Manhattan
I think it's only for the electives. After electives, you go into concentration.
Oh,
Mostly will be in Manhattan or Dobbs, right?
okay. All right. Well, let's say, all right, so I've got these students broken down by either Manhattan students, Dobbs Ferry students, or Bronx students. And we'll say that's your preference. Like, you're everywhere
okay.
because you have to be. We'll say, would your preference be Bronx?
Yes.
Yeah.
Okay, so we'll call you Bronx students. And let me ask you, do you think Mercy College provides an adequate selection of course offerings? You say no.
No.
Henry, I'll let you know. Yes, no, Henry?
I'll say no to it.
Okay, everybody, so 4 out of 4 say no. Suppose we ask all the Bronx students, 61% say yes, 49% say no. And then we go do the same test in Manhattan, and 89% of those students say, yeah, provide excellent course selection. I don't know what the Bronx students are talking about, it'll be fine. The same in Dobbs Ferry, 77% say yes, adequate course selection. So, those are the numbers. Let me ask these 2 questions. All right, so 3 questions the chi-square test can answer for us. Number 1, are the 3 true population proportions different? What do I mean by true population proportions? So we've got 3 sample proportions. We've got a sample of Manhattan students, sample of Dobbs Ferry students, sample of Bronx students. And this is a proportion, right? But this represents a whole population. This is just a sample of 100 students at each campus. So we don't know if the true population proportion of Manhattan students who think there are good course offerings is really 89%, or if it's something else. You with me to there?
Mhm.
This is just a sample. So let's ask the question, are the 3 population proportions different? Now looking at the data, the sample data, what would your initial answer to that question be?
You would say yeah, but it shouldn't be.
They're different. Okay, you say different for 2 reasons. 1, I assume because the numbers are actually different. And 2, because you know it makes a difference. But we'll concentrate just statistically on the first thought. We look at the numbers and you see that they're different. But we need to do some more research to really say that they are truly different. The way we did this with proportions is we did confidence intervals. We say 89 is our point estimate. but I'm 95% confident that the true population proportion is between this and this. Remember that whole deal? So you would need to do something like that before you could say statistically, you need to do that with all three of these.
Right.
Before you could say, I am, at the 95% level, I'm statistically confident that these proportions are actually different. You need to do something like that. Alright, now chi-squared is just a different way of answering that question. It's a more succinct way of answering that question, and like I said, if you're giving a presentation, you say I did a chi-squared test and determined that these population proportions are different, then sometimes that can give you a little bit more credibility. Also, when you give somebody confidence intervals, when you start explaining that, all right, here's how the confidence intervals work, one, in a way, it sounds more complicated, but it's like a double negative. It sounds more complicated, but sometimes people listening to you think they understand statistics just based on your description of it, and then they might start arguing with you on the confidence intervals. So it's like you're giving them enough to be dangerous with the confidence intervals. If you just give them the chi-squared test, they're like, oh, okay, all right, done. Problem solved. All right, so question 1, are the three true population proportions different? We will learn the chi-squared test for differences in population proportions to answer that question. Number 2, are student opinion and location independent in the true population? What do I mean by independent?
Does it
It
depend on
doesn't
variable?
depend on,
That what doesn't depend on what?
the opinion of the location does not depend on whatever the decision was, I think.
Yeah,
Something.
okay. Can you be more, you've got the right, you're adding and, put the parts together for me, you got them all there.
Alright, so the opinions and location of the students does not depend on,
It's just, it's opinion and location of the students, one of them depends on each
Yeah, I
other.
was gonna say the student is the location, the student opinion depends on the location.
Okay, yes,
Oh,
yes, so
okay.
student opinion depends on the location.
Yeah.
Alright, that would mean that they are not independent, that they're in fact dependent. And that's probably what we would guess, right? That your answer to this question depends on which location you prefer. So we would say that they are dependent, we'd probably say they are not independent. And we could answer that question with regression analysis, just like we learned over the last 2 weeks. We have some ways of figuring that out. We could also answer that question with our chi-squared test for independence. Now the good news for tonight is that these two, chi-squared test for independence and the chi-squared test for differences in population proportion, are exactly the same. They're just the same calculations with a slightly different interpretation. One says, all right, the population proportions are in fact different. Well, if they are in fact different, then that means it depends on which location you're in to determine your answer.
Can I ask a question that may or may not make sense? If you were doing like the survey, obviously, when you were doing this and you were gonna ask for about location, like does location matter to you? Is that the yes or no answer? So does that become the dummy variable or something?
This is a good question. I was afraid someone was gonna ask that.
Obviously.
Alright, so I was thinking about that and I don't know. I've never really done regression analysis where you have, and you can, there has to be a way to do it. So you would ask yes or no questions and how we would graph that, and we would have 3 locations. Alright, so maybe we would have like location here, alright, location, and we would have opinion, Alright, so your opinion is just gonna be yes or no, okay, and we'd have 3 locations, 1, 2, 3. And so what you might find is, a bunch of dots here, a few dots here, a few dots here, a bunch of dots here.
Basics all over the place.
1 dot here, and a bunch of dots here. Well, it's not all over the place, right? Because for this one, you have almost every single dot up here, and only one dot up here. For this one, you have most dots here, some dots here. For this one, you have most dots here, some dots here. So Excel would interpret that, right? What's the variation? Can we explain why there are more dots up here, and almost all the dots up here, and more dots down here? And we would have the same performance measures that we had the last couple weeks. Are we able to explain the variation? Well, it doesn't explain every single person, but explains X percentage of them, yada, yada, yada. All right. Okay, so as I mentioned, these two tests are the same, right? Because the population proportions are not different. Then that means it doesn't matter where you go to ask the question. You could go to Dobbs Ferry, you could go to the Bronx, you could go to Manhattan, and the answers would be the same. Another way of saying that is the proportions would be the same. So these two are the same, they're just used for different purposes. Last thing chi-square might tell us, if I were to say that the true population proportion of Manhattan students who say that they're good course selections is 94%, Dobbs Ferry is 83%, Bronx students is 68%, I'm just putting in some numbers. If I were to say that these are the actual numbers, all right, I'm saying that's my hypothesis. These are the real numbers for the true population. And then I look at the sample data, which is different. All right, sample data is different from these numbers. Does the sample data prove me wrong? Everybody with me there? So here's the sample data, 89, 77, 61. Before I collected the sample data, I said, I think the numbers are 94, 83, 68. Those are different, right? Okay, so am I wrong in having said this about the true population?
You don't know what your significance level is, right? Like where it mattered?
Exactly, that's the kind of thing I need, right? I'm saying that this is the true population proportion, right? These numbers are different from what I say, but these are just sample numbers. So in reality, I could still be accurate about this. I would just need to see how different the sample is, how likely it is, based on significance levels, and what threshold I'm willing to believe of unlikely events. And I could use things we've already talked about to answer that question. Or I could use what's called the chi-square goodness of fit test. So this is what I say the numbers are. Does my sample data fit my hypothesized statement about the true population? Alright, so I'm not sure how well that last explanation went. Let me tell you one thing and then make a couple of comments. The one thing I want to tell you is we're just going to talk about this briefly. We're not going to actually do the calculations for this. But I still want you to understand that it's something chi-square could be used for. Alright, so if that makes you feel good, I'm glad. Now let's just make sure we understand what it's saying. So I make a statement of what I think the true population numbers are. I say it's 94, 83, 68. I go out and I get some sample data. Are my predictions correct? Tell me. Are my predictions correct?
You have to use the chi-square good of fit stuff.
I could use that, or I could use confidence intervals, I could use something else. Alright, but just looking at it, does it look like I was right?
No.
Not quite right. I was off. Or was I off by enough to say that I was wrong?
But we don't know what number, but we gotta find the number.
We gotta find all that number. Okay, you all have it. I was just a little nervous when I didn't see enthusiastic smiles with that one. So that's goodness of fit test. And that's all we'll talk about for goodness of fit. So you will learn these two, and if you ever need to use goodness of fit, you can just flip back to the textbook. It is fairly simple, it's just a slight variation of this test, or these two tests. Alright, we will concentrate our efforts tonight and the chi-square test for differences in population proportions, chi-square test for independence. So let's do that with this example. All right, so first, chi-square test for differences in population proportions. I mentioned we already have alternative means of determining population proportion differences. They are our proportion confidence intervals, our proportion difference confidence intervals. We've done that, and you're familiar with that. We're not going to use that. We are in fact going to use the chi-squared test to solve this problem. We're going to state a null hypothesis that all the true population proportions are the same. True population proportion of students in the Bronx, Dobbs Ferry, all
Let's-
equal each other. The alternative hypothesis is that not all the population proportions are the same. At least one of them is different. And if we reject the null hypothesis, that will mean that at least one of the population proportions is different from the others. Are you with me? So null hypothesis says they're all the same. Alternative hypothesis says at least one is different. Okay. How do we do this? Let's create a table. Let's create a table of who said yes, who said no. Let's sum everything up. The next thing we're going to do is we're going to say if the null hypothesis is true, what would we have expected each of these cells to be? So, and then after we do that, we're going to say what's the difference between what we observed and what we expected. And we're going to say, is that a large difference? If it is, then we can reject the null hypothesis that they're all the same, assume the alternative that at least one is different. Make sense?
Or fail to reject.
Yeah, we may fail to reject. And we may say, well, they could all be the same, even though we got slight variations in our sample. So we're going to put these in a graph. We're going to sum everything up. We're going to say, if the null hypothesis is true, what would we have expected to see in each of these cells? Compare that from what we actually saw. Say, is that difference enough to reject the null hypothesis? Alright, so anytime we're doing a yes-no question in a chi-squared test, we put the number of yeses, number of no's, total number for each row, and for each column. Okay? Then, as I mentioned, we now want to ask ourselves, if the null hypothesis is true, what would we have expected to see in each of these cells? So the null hypothesis says the proportion of yeses should be the same in Manhattan, Dobbs Ferry, and the Bronx. So what would go here? What would we expect? What number would we expect in each of these cells? And I'll give you a hint. It's going to be the same for all three of these. Because the null hypothesis says the proportion of students who say yes should be the same in each cell.
It would be like the average of the expectations.
Yeah. What would it be? Tell me the number.
That's a guess, I'm sure. What is 75?
75?
0.6?
75.6. That sounds right to me. 75.6. Alright, how we would do it specifically is we would say 227 out of a total of 300 people said yes. If all of these proportions are the same, then we would expect an equal number of those 227 to be from each campus. So we could take 227 divided by 3, I think that would work. Does that give us a 75.6?
Yeah.
Yeah? Okay. Another way we could do it is we could take this column total, 227, divide by the grand total, so 227 out of 300, that gives us the proportion who say yes,
Mm.
and then we just multiply that proportion times the row total, 100. So this is the proportion who said yes. How many students in Manhattan were there? That would be it. Alright, so what's my next slide, Joe? To fill that in, 75.6. Pi squared, oh no, okay, yeah, so 75.6. 75.6. 75.6. Alright, now, the reason the proportion should be the same in each, but the reason the actual numbers are the same is because we had the same sample size in each location. They could have been different. Like the proportion would be the same, but the actual numbers would be different. In this case, I just want to make it easy. Proportion is the same and actual numbers are the same. Okay, and how many, what proportion would we expect in each cell for the no's?
$24.3.
24.3? Alright, I'm a little concerned that the 0.6 and 0.3 don't add up to 1. Is that, will we let that go for now? 3. You know, see what I'm saying, right? Like, what happened to the 10?
24.4.
24.4? You like that? Okay. 24.4. 24.4. Alright. The way, I think the best way to think about it is, alright, let's take the column total divided by the grand total. So 73 out of 300 students said no. What proportion is that? That should be the same proportion for each campus. So that proportion times this 100, that proportion times this 100, that proportion times this 100 gives us 24.4. Alright, so we have our observed, we have our expected, and now we need to take the difference. We need to do some calculation to quantify the difference. Number of ways we can do this, but the statisticians worked out this chi-square distribution for us. They're going to tell us how we take the difference, and they're going to tell us what would be unusual given the sample size, given the magnitude of difference.
So obviously there's a degree of freedom somewhere involved.
Yeah, so there'll be a degree of freedom, and there'll be an exact way we calculate the difference. Alright, there's different ways we could calculate the difference between observed and expected, but they're going to tell us how, and they're going to tell us what would be an unusual answer based on that way of calculating. That way of calculating is observed frequency minus expected frequency squared. We don't care so much if it's a positive or negative difference. Square it, divide by the expected, add that all up, rows and columns. In our case, we have 6 cells. We just do that 6 times, add all 6 together.
Excel does that, X2 stat.
I have had some students complain that Excel doesn't do that automatically based on the formula that you get from the textbook. I find the best way to do it is just do these calculations manually on Excel and just kind of, what's it called, just pull the formula down and pull the formula across, make sure it's linked correctly. Alright, so let's calculate the chi-squared test results for each. So, let's see, so you can keep, why don't you keep this page open in your text, and then we'll go back to this page. Alright, what did we say the expected was? It was 76.4, I'm sorry?
76.6.
76 point,
75.6.
oh, 75.6, okay. 75.6, and this was 24.4, okay. 75.6, 75.6, 6, 24.4, 24.4. Okay, so, can we do that? Can we calculate the chi-squared test statistic 6 times? So, maybe we can divide up these cells. Like maybe Henry, can you do this first one? Henry? Michael, can you do this one?
Second one? Second,
Yeah.
yes?
Michael.
Using the formula?
Yep, yep. And then Catherine, can you do this one? Calvin, can you do this one? Alright, so we're going to take observed minus expected, square that, divide by expected. And then you're done. And if you get done, maybe somebody can start working on these last 2 cells.
Expected would be the 75.6.
Yes.
I got, 0.0259.
0.026.
Yeah.
Okay. There or not. You want to start working on this one, Michael?
Yeah.
Just in case you got that first one wrong, we'll give you a shot at redemption.
Why is it doing that?
61. Um, 2.819, 2.82.
Excellent, excellent. Anybody else?
7.35.
7.35. Alright, Catherine, you want to start working on this one?
I got you.
0.085.
0.85, okay.
2.38.
2.38? Alright. Alright, I'll leave the names up there for accountability.
8.73.
8.73. Okay. So can we add all 6 of those together? Can someone do that?
All 6?
Yeah, add all 6 of them together.
Yeah.
Yeah, 2.83 plus 7.35 plus 0.06 is 0.026.
Can you slide over?
Sorry.
21.391.
21.39.
Yeah.
Okay. Right. Moment of truth. Alright. Now you're looking good. Yeah, alright, so right on, pretty much. Right on, pretty much. Right on. Right on. A little off maybe. Alright, right on. Right on. Right on. Everything looks right on. Right? Okay. We add them all up and we get 21.435. Alright, so we have calculated our chi-square test statistic. Now, we need to look at a distribution and say, is that chi-squared test statistic unusual given that the null hypothesis is true. So, we need a degrees of freedom. We're gonna look in the back of the book and see if our test statistic is past what we would call a critical value for chi-square. Now, chi-squared works very similar to other distributions we looked at. It says if all the proportions are equal to each other, we wouldn't expect them to be exactly the same in every single sample, right? We wouldn't expect zero variation. That would be totally weird. Imagine that. Like, you know, every sample you get is exactly in the true population proportion. We would expect some variation, so we have a peak here. Every once in a while we would get this much variation. Every great once in a while we get this very much variation. And every once in a blue moon we might actually get this much variation. And we could say that the null hypothesis is still true, we just got a whole lot of variation. Other conclusions, we could say we're not willing to believe that, we would rather say the null hypothesis is false. Degrees of freedom. Rows minus 1 times columns minus 1. And by rows and columns, we mean the relevant cells that we calculate the test statistic for. So we have 3 rows, 2 columns, 3 minus 1 is 2, 2 minus 1 is 1, 2 times 1 is 2. So for this test statistic, we have 2 degrees of freedom. Suppose we like a significance level of 5%. Let's flip in the back of the book and see if we can find a critical value.
0.103.
Point? No.
No.
No. It's going to be, is it? No.
2 degrees of freedom, you said?
Yeah, 2 degrees of freedom?
0.95.
0.95? I don't like it. I want like 4 or 5 or 6 or something.
5.991?
You like 5.99?
Am I on the right?
Oh, you're looking at the next slide? Okay, fine.
Oh, 5.991.
Alright, well,
Yep, I was right. See
yeah,
that?
but it's more important, Michael's got the right idea, because
Yeah.
he's looking at the table, and that's what you need to get used to doing.
Well, yeah, sorry, because it
No,
it goes 0.995 down to 0.90, and then it stops, and then goes from 0.10 up. So it's-
Which table do you look at?
so I didn't look up 0.05, I looked up 0.95.
no. Alright, fair enough.
Yeah, 5.991.
Alright, so yeah, check it out. Henry, see if you can look, practice it.
Yeah, that's different from the other
Right, explain to Calvin what you did wrong, and then maybe,
That's
They'll get-
different from the other tables, though.
yeah, it's, you know, it's nuances of difference.
So chi-square distribution?
So I looked
Yep.
up 0.95.
You're supposed to look up here, right?
Yeah,
So we're looking at 0.95.
Yeah.
So degrees of freedom.
5.991.
No, you're looking at, so how area and upper tail would be 5%. So you go over to the 0.05 column,
Oh, okay.
and then you go down to 2 degrees of freedom.
So 2 degrees, okay.
Does that make sense?
5.991.
Yeah.
You got it, Catherine?
Yeah.
Alright, so
Got it.
in our, did I do it? Did I do this thing? In our example, we would say the critical value is 5.991. Anything beyond that, we would reject the null hypothesis. And it was way beyond that, it was like 21.3. So what is our conclusion? The brick. We reject the null hypothesis. What does rejecting the null hypothesis in this case mean?
That we are 95% confident that, something.
That they're not all the
The
same.
proportions are not the same, the population proportions are
The
not.
true population proportions are different. At least one of them is different. Okay, so whoever told us that the proportion of students who like class selection in Manhattan, Dobbs Ferry, and the Bronx is exactly the same across campus, in our opinion, was wrong.
Very wrong.
Yeah, that is wrong. There's a difference. Alright, there's a difference in the opinion of Manhattan students versus Bronx students. At least one. There's at least one difference somewhere. Alright. So we got our test statistic, we calculate, 21.4, we calculated our degrees of freedom as 2. We looked in the back of the book on the chi-squared table, we found a critical value of 5.9. We decided to reject the null hypothesis and assume the alternative that not all of the population proportions are the same. We found enough difference between the observed and the expected to say conclusively, in our opinion, that not all the population proportions are the same. Got it? Make sense? Alright. So we move on now to the chi-square test for independence. Now the good news here is, remember I told you this is the exact same test? Because if they are different, what does that mean as far as independence, dependence? If the Bronx students have a different opinion than the Manhattan students, then that means opinion depends on location. So that means they are not independent. So if we have a hypothesis test that says the factors are independent, do we have overwhelming evidence that this is not true?
Yes.
We do. Whoever says this, that they're independent, is essentially saying that the true population proportions would be the same for all 3 groups of students. We found them to be different, and we found them to be significantly different, that we were comfortable rejecting the null hypothesis. Now, in past classes we have learned different ways of doing this. We learned regression analysis. I gave this example. We could see a regression analysis like this, and we could say, unexplained versus explained. This would be cumbersome to try to explain. Unexplained versus explained, standard error of the estimate, correlation coefficient, would, I think, be rather difficult to explain in this particular case.
You gotta draw your line.
Yeah, it's like, whereas you have to explain, it's not quite a line, you just have a lot to explain. You have a lot of caveats, you have a lot of those performance metrics to say, well, what you would expect and what's different. Chi-square takes us right to it. It says, boom, we did a chi-square test for independence, the null hypothesis was rejected at a significance level of 5%. It probably would have passed a 1% test, because 5% test had passed out of the ballpark. A 1% test probably would have passed as well. We could have also done this, as I mentioned, with confidence intervals for proportions and proportion differences, but now we know chi-square. Alright, once we reject this null hypothesis, that means that opinion is dependent on location, which we think is true. The chi-square test statistic and critical value are calculated the exact same way as in the test for differences in population proportions. Any questions? Alright, so the rest of class is just slides to support what we did, and then I have an example of each one. So, you made it. Got the material. All we need to do is just sit, absorb it a little bit, practice it, and we'll be golden. Okay, and then I mentioned this goodness of fit. I told you I would just explain it to you, which I think I did, and we won't talk about it again, but goodness of fit, you should just remember, I could crack open the textbook and learn how to do that if I want to, but I'm going to concentrate just on the first 2 tests. Alright, so let me show you some slides to explain the chi-squared distribution, some slides to explain the chi-squared test for differences in population proportions, chi-squared test for independence, and we won't talk about this one anymore. Alright, chi-squared is made up of the sum of squared deviance, so we took observed minus expected and we squared that. Shape of any particular chi-square distribution are determined by degrees of freedom. Number of independent terms is included in this sum. So we just had a yes or no answer to our question, but we could have had multiple categories. We could have had, multiple rows, multiple categories. and we will, the more categories we have, the more cells we have, right, sort of the higher we would expect that chi-squared distribution to be, the higher we would expect that critical value to be. So if you were to look at the chi-square distribution, and you were just to move your finger down the column on degrees of freedom, you would see that number getting bigger and bigger. And that's fine. The statisticians just calculated it. You tell me how many degrees of freedom you have, I will tell you what would be unusual in those cases. All right, so I mentioned earlier, all right, we wouldn't expect the sample to be exactly the same as the true population. Zero variation would be weird. We would expect some. Every once in a while we get this much, and we have what we consider highly unusual based on our significance level, based on our degrees of freedom. Our null hypothesis for this test will always be population proportion 1, 2, 3, etc. are all the same. Alternative hypothesis, at least one of the population proportions are different. Rejecting the null hypothesis, as I said, means at least one of the population proportion is different from the others. Summary. So, we show a table of observed frequencies. That was our starting point. We had the observed sample data. And then we created an input for what we would expect, expected frequencies. Then we calculated the chi-square value, observed minus expected squared divided by expected. We added those all up, and we applied our decision rule. We did the critical value rule, based on our critical value of 5.991. We could also have done the p-value. When you calculate this out in Excel, Excel will give you a p-value. If the p-value is less than your significance level, throw the brick. This gets more and more confusing. It's like, who do we throw the brick at? In this case, is when we start asking the questions from different angles. So, reject the null hypothesis. All right. So, expected. Remember I said, how do we calculate the expected frequency? And it's just an average. All right. If the total number of people who said yes was, I think, 277 out of 300, how many would we expect in each of those categories? The technical way we did it, I said, let's take the column total at the bottom. Let's divide that by the grand total, which is in our example was 300. And then let's multiply that by how many people we asked at that campus. In each case, it was 100. Then the difference between observed, expected, squared, over expected, add those all up, is our chi-squared statistic. Okay, I hope that wasn't confusing. That was just slides for what you already know. Now we'll do an example.
Sure.
Let's take a look. Alvarez Communications has just received 3 shipments of cell phones that it uses in its assembly process. Each shipment is from a different supplier. You want to test the proposition that the proportion of defective shells is the same for all 3 shipments. You select a random sample of 200 shells from each shipment and find the following number of defectives. Shipment 1 has 6 defectives out of 200. Shipment 2, 26 defectives out of 200. Shipment 3, 22 defectives out of 300. Conduct the proper hypothesis test using a significance level of 5%. All right, so you've got these 3 shipments, cell phone shells, and you want to see the defective rate. Now you set this up as a null hypothesis. You want to test the proposition that the proportion of defective cells is the same for all 3 shipments. So why would you set up the test like that? Say it's the same for all 3. So if they're the same, that's your null hypothesis. What's your alternative hypothesis?
But they're not the same.
If they're not the same, okay? And remember, the alternative hypothesis is something for which we need overwhelming evidence. So that might be why we set it up.
Oh, because we want to see which supplier is better.
Yes, and we want overwhelming evidence that there is a difference between these suppliers. All right, so just looking at it, who do we like better off the bat?
One.
Yeah, we like one, but this is just a sample, all right? It could be that all three of these suppliers are the same. Let's see if we have enough evidence to say that these proportions are statistically different. All right, so first we set up our table. Observed frequencies, 6, 26, 22, total of 200, so we have non-defectives. Put them all in the table. What do we do next?
Expected.
18
Expected, is that what you get, 18?
quad, yeah, 6 divided by 18.
All right, I think I left these next to blank, oh wait, no, okay. So we've got our null hypothesis that they're all the same. Alternative, not all the proportions are the same. And I think I left these two blank for you. Let's see if we can fill in the expected frequencies. And then let's put a full table of observed and expected. Put observed here, expected here. Then let's calculate the chi-squared test statistic for each of the 6 cells, add it up, and see what we get.
Can you go back to the actual?
Yes, yes. All right. So, give you a couple minutes to work on that.
How do we get the expected again?
Alright, expected, the trick is column total divided by grand total gives us the proportion we would expect in these. So column total divided by grand total times row total. So 54 divided by 600 times 200 gives us this. 54 divided by 600 times 200 gives us this. Does that make sense? You could do the same thing for this, but you just know it's the opposite.
Okay.
Whatever's left over. You could, if you want to get crazy, you could open up Excel and do this. Yeah? Alright.
sorry, so you said so it's 54 divided by 600 times 200?
Exactly,
And then we'll get it for 1, 2, and 3?
exactly. Because these are all 200,
So it's all gonna be the same number?
yep. Exactly. It's the reason it's the same number, because these are all the same.
Oh, okay, okay.
Smooth sailing, Matt.
Hmm?
Smooth sailing.
Yeah, I think so.
Hold on. Sorry.
Yeah, 24, I'm pretty sure I did it right.
And the critical value is, I guess it's the same as last time, right?
Yeah, 5.9.
So,
Brick.
brick. As life goes on, it becomes more confusing who we throw the brick at.
Eventually everybody will discuss it.
Well, because in this case,
Yeah, you don't know if it's
Right.
good or bad.
well, we're setting it up so that we have overwhelming, we throw the brick at the bad supplier, maybe? I guess, yeah, that's what it would be. So,
Or
in our first,
you know, throw the brick at the person who chose the bad supplier to buy from, without doing their due diligence first,
Okay.
wasting money.
yeah, okay, I guess, yeah, brick would be legitimate and the bad supplier. Because if it doesn't, if you fail to reject the null hypothesis, then you might have to admit that these are the same. You know, that it's just an anomaly, that the sample was a little bit different, and supplier 2 could be just as good as supplier 1. Alright, how's everyone doing? Still working? Ready to take your time. I'll send a text message, check Facebook. ready?
Yes.
Alright, I actually stuck these slides at the end, because I didn't want you to be distracted by them. But I've got them all here. Alright, these slides you have on your paper, on your printout, but they're at the very end. So I calculate expected number of defectives, assuming the null hypothesis is true, at 18 for each shipment. You like 18? Which would mean 182 non-defectives for each shipment. So we put all the observed and the expected on one table together and makes it easy for us to do the calculations. So observed minus expected squared divided by expected.
Oh, snap.
Oh, you forgot to square it? Alright, well, it's good you learned that lesson, and from now on you can just fire it into Excel and we'll do it for you. I get for the full table of chi-square calculations, I get these, and I get a chi-square test statistic of 13.67. Do you agree?
Yeah.
Do you agree?
Little off.
Little off? Do you agree, Calvin?
Little,
Alright, fair enough. And Henry, I'm sure would agree. A minor adjustment to the math. Now, our chi-squared test, our critical value is the same as it was last time. So we have 3 rows, or 3 columns, 2 rows, 3 rows, 2 columns, so 3 minus 1 times 2 minus 1 equals 2. If we like a 5% significance level, 2 degrees of freedom, critical value is 5.99. 13.67 is way past 5.99. If we were to put this in Excel and ask for a p-value, we would get a p-value of 0.0011, which is so much less than 0.05, we would reject the null hypothesis. In this case, what does it mean that we're rejecting the null hypothesis?
they're not the same,
That they're not the same, yeah. That the true population proportions are not the same. So supplier number 2 can't come to us and say, the true population proportions of my cell phones, shells, and everyone else's are the same. It just so happens that I got unlucky at this sample. That's why I had more defectives. Right? What do we say to that supplier when they come to us and say that?
Oh, shit.
No, we say no. Exactly. I ran a chi-squared test. Excuse me.
You said.
And I have
Liar.
statistical evidence at the 5% significance level. In fact,